So this is chapter 25, electromagnetic induction and electromagnetic waves. I should caution you, this chapter is very, very long, much longer than the previous chapter, so just be aware of it. Okay, this is what we're supposed to be learning. We want to understand the circumstances under which changing magnetic fields lead to currents, induced currents. Understand how the movement of a conductor through a magnetic field leads to a motional EMF. We'll explain. Like a voltage, right? Remember, EMF is like a voltage. Use Lenz's law and Faraday's law, so there's two new laws of nature, to determine the direction and size of induced currents. Understand how induced electric and magnetic fields lead to electromagnetic waves. Apply wave and photon models to the electromagnetic spectrum. Understand the properties of different types of electromagnetic waves. So this, like I said, this chapter is crazy. I mean, usually this makes up one chapter. This is a completely different chapter, but they're just sticking it all together in this chapter, so it's really, really long. All right, so let's talk about the induced currents. So we've had a chapter on magnetism, and we learned that magnetism is produced when we have a moving, charged object. Okay, so for example, an electrical current. So electrical currents produce magnetic fields, or magnetism. So we can say that, okay, remember B field, that's magnetism. So currents, electric currents, produce magnetism, which is what we saw. So here, what we want to talk about, here's the question. Does magnetism produce currents? Right? That's the question. Now think about it. Just say you lived, hundreds of years ago, before we had electric lights and all that. People are discovering that, how to do this, but wouldn't it be great if this were true, if you can use magnetism to somehow produce a current, so you could have, wires everywhere and light up the world? I mean, wow. So this has enormous practical importance, Can you use magnetism to produce electrical currents? That's incredible. All right, well, obviously I wouldn't be talking about it unless it's true, right? So we're going to learn about how we can use magnetism to produce electric currents. We'll talk about two ways of doing it, and we're going to refer to these again and again, so pay attention. All right, so here's the first one. This is called the Faraday experiment. So here, this is just a coil of wire. It's a coil of insulated wire. So it's one really, really long insulated wire just wrapping around, but it's one wire, again, insulated. This is just something that measures current. Now you can see I don't have any batteries, right? I don't have any power supplies, so, I don't have any way of making a current, right? Because I don't have any batteries or anything like that, but you watch. Okay, this is a magnet. So watch what I do, and also watch this. So again, this tells you the current. I have to press it. So kind of keep your eyes on this and what I do. Okay, watch. My goodness, I'm producing an electrical current, right? Okay, how about if I wish I had 3 hands. Okay, I'm going to keep this still and move this. I still get electrical currents. How about if I go like this? I get electrical currents. But how about if I just do this? I take this and I keep it stationary. Am I getting any electrical currents? Am I getting any electrical currents now if the magnet is stationary relative to the coil? Not at all. I only get electrical currents if the magnet is moving relative to the coil, if the coil is moving relative to the magnet, or if there's some kind of the angle is changing. All right, so what do you know? We can make currents from changing magnetic fields. Now, this current that we just produced over there, it's not a current, like I said, from a battery or from a power supply. It's different, right? And so what we call it an induced current, right? We induced the current using a changing magnetic field, right? So that's why they call it induced current. You know, like a pregnant woman, you know, when they need to induce the child, they need to get that kid out of there, right? They give her drugs or whatnot to induce the birth, right? To hurry it up along, you know. It's not natural. But it's natural, but it's induced. Whatever. I don't know. All right, so we call it induced current. Okay, so that's one way, right? Now, wait a second. This is incredible. You know, we produce a current, right? So that means that, you know, in reality, there's electrons flowing through those wires. Or like how we like to think of it, there are these positive charge carriers moving through the wires, right? Well, what's making them go around? There has to be a force, right? Well, don't forget our famous equation, F equals QE. So if there's a force making these charge carriers go around the wire, guess what? There has to be an electric field also. So what did we produce? We produced an induced current and an induced electric field. So that's incredible, right? So what did we just do? We created what's called a generator, right? I mean, I had to work, you know, I had to, you know, move the magnet or move the coil or something like that. So basically, what we did, we converted mechanical energy into electric energy. And that's what a generator does, you know. Electric generator, they produce electricity, but by some means. So we use mechanical energy to produce electrical energy. A generator. So we made a generator. Awesome. Okay, so that's one way. Now let's talk about another way. And the second, what I'm going to talk about now, we're going to discuss again and again and again. We're going to just keep looking at it in different ways. Okay. And the second one, this one here, it's nice because we get to use a lot of the things that we learned in the previous chapters. So it's kind of nice review. Okay, so this is called motional EMF. You'll see why. So motional means motion, right? EMF is like voltage. Okay, so what do we do? Or what's going on? So here we have this external magnetic field. And remember, the X means that the magnetic field is going in, you know, in. Okay, this is a piece of metal, conducting rod. And initially, you know, it's neutral, right? It's neutral. And we're going to just say it has like positive charge carriers and negative charge carriers. Okay, what we want to do is somehow, which we'll get into, move this piece of metal to the right. Right? So what are we doing? We're moving charges in a magnetic field. Now hopefully you remember when you move charges in a magnetic field, there's a magnetic force on those charges, right? And we learned two ways of writing that. FB equals QV cross B, right? That's the direction. And then with the magnitude is QVB sine alpha, right? Where alpha is the angle between the QV and the B. Okay, so look. Here we have charged particles moving this way in a magnetic field that points that way. So what you need to do, please, figure out what happens to the pluses and what happens to the minuses. And don't just wait for me to explain it. You figure it out on your own using this. So figure that out. So pause your video and figure it out. Okay. Let's talk about the pluses. So QV is positive, points to the right. B is this way, so QVB, so the force is up. So all the pluses feel a force up. Well, therefore, what do the minuses feel? A force down. So what does that mean? It means all the pluses are going to go here, all the minuses are going to go there. Well, what did we learn about that a long time ago? So we have a charge separation, right? Pluses and a minus. Pluses here, minuses there. So that means there's a potential difference. There's a voltage. It's like a battery, right? Remember what a battery is. A battery uses chemical processes to separate the charge. So you have pluses and a minus. So we have a potential difference, a voltage. Okay, a voltage. Wow. And it's induced, right? It's induced. Well, wait a second. If you have a voltage, you have an electric field. So what did we just produce? We just produced an induced voltage, an induced electric field. Wow! Just by pushing a silly thing in a magnetic field, right? Oh, sorry. Okay, now I got to just digress for a minute. This is called, all right, just digress for a minute. Quite a while ago, we talked about batteries, right? We discussed batteries. And we said that there's this thing called an EMF, which is the work per charge required to separate charge. Remember that? Now, for an ideal battery, this is the same thing as voltage. But we wanted to use this term because, like for a battery, you know, the work is done by chemicals to separate those charges. And we didn't go into detail. There's no reason to. Okay. Now, this is really a very general equation. This is the work done by any force to separate charges, right? So for this, you know, I had to apply a force to move this thing, and then there are magnetic forces to separate the charges. So it's probably better to use EMF than delta V, but we might use either one of them, okay? So there. Okay, so we really did use the magnetic force that was separating the charge. All right, so we're going to use this a lot. All right, EMF, because it's general, you know. Anyway, that's very nice. Okay, so ta-da! So we have an EMF. In our heads, we think voltage, and we also think it's related to electric field. Wow, like a battery, right? It's like a battery. Now, just for fun, let's make a complete circuit. Let's connect a wire or something like that. Okay, conducting rail, right? So this is basically a wire, you know, conducting rail, wire. So now, look, I have a complete circuit, right? Right here. This thing acts like a battery because I have separated charge. Now I have this complete circuit. So, what happens? What happens when you attach a wire to a battery? You get a current. Agree? You get a current. All right. And now what's going to be the direction of the conventional current, right? The conventional current. Remember, conventional current is the motion of the positive charge carriers. So it's going to be like this, right? The positive charge carriers don't want to be up here. They're repelling each other, so they want to be down here, so they're going to go like that. Okay? So we're going to get a current. And if we attach a light bulb, we're going to get the light bulb is going to produce light. Okay? So ta-da! So this is the second example of how this is just a generator, right? We had to do some work to move this rod, this piece of metal here to the right in the magnetic field. As soon as we did it, we get a current. Again, we can call it induced current, induced voltage, but now we're going to say EMF, whatever, induced electric field. Wow. Okay, so 2 examples of generators. Now, let's keep going. This piece of metal kind of acts like a wire, right? You know, you can just assume this is a wire too. Okay, so here we have a current going this way, and it's in a magnetic field. Now, what did we learn about wires in magnetic fields? Are there any forces? Okay, is there a magnetic force on this conducting rod, which I'm saying you can just treat as a wire? And if so, what's the direction? Okay, so now you have to use that other formula. Remember, there are these 2 force formulas. This is with moving charges, then the one with the wire was FB equals IL IL cross B. Or we had FB equals ILB sine alpha. Remember that one? All right, so let's do it. So IL points up, right? IL points up, B is in, so B is in, so where's the thumb point? That way. Okay, so there's a force on that rod or wire that points to the left. Now, that makes totally good sense. Because think about it. Let's just pretend it pointed to the right. Then I would have invented a perpetual motion machine, right? In other words, if I start moving it to the right, and there's a magnetic force to the right, it just keeps on going, right? I can just let go and just keeps on going, perpetual motion. Doesn't happen, energy is conserved, sorry, So in other words, I got to keep pushing it because the force is to the left. So bummer, no free lunch, okay? No free lunch. All right, now let's go back to these separating charges. So I have a whole bunch of pluses up here, a whole bunch of minuses up here, down here. Now, do they want to be separated? No, right? Unlike charges attract. So they don't like being separated, right? So the more positives you get here and the more negatives you get here, there's going to be a stronger and stronger electrical force, right? Electrical attractive force. But, the magnetism is keeping them away. Well, you have to admit, eventually, you're going to have so many pluses and so many minuses that the electrical attractive force is going to equal that magnetic force, all right? So that's called equilibrium, right? So we're going to say that the magnitude of the electric force is going to equal the magnitude of the magnetic force, okay? So let's see what happens. So when that happens, because remember, electricity wants to put them this way, magnetism wants to pull them that way. So eventually, those forces are going to equal, and no more charge separation after that. Let's just see what we come up with. All right. So what's the electric force equation? F equals QE. So we have QE. And we'll just say it's induced, because it is, right? We'll just call it induced. Okay, now, a long time ago, you learned that for a while, I want to put this in terms of the EMF. You'll see why. So I'm going to say that is equal to the induced EMF divided by the length of the wire. This is L, right? So the length of this, I'm calling this a wire, right? Okay, so the induced EMF equals the induced E field equals the induced EMF divided by the length, all right? Okay, so that's the electric part, right? That's the electric part. And I want to say that, so that's the electric force, right? That wants to pull those guys together. And then we have the magnetic force, which wants to push them apart. And again, the force is QV cross B. What's the magnitude of that? Magnitude is just QVB sine alpha, right? But what's the alpha? Well, the V is this way, the B is that way. So what's the angle between this and this? It's 90. Sine of 90 is 1. So I don't have to worry about that. So I'll just say QVB. Okay? So the electric force in the brown equals the magnetic force in the green. And therefore, we can do a little math, see what we come up with. And therefore, let's see, let's just use this one, because I want in terms of EMF. Get rid of the Q. Multiply by the L. And I have, there we go. So the induced EMF, which is like a voltage, equals the velocity of the bar, or the wire, sorry, the B field, and the length of the wire. Okay? Wow, that's it. So this, again, we're going to use this again, so I'm going to write it up here. Induced EMF equals VBL. So that's all you need. I mean, think about it. This is just a, this is like making a battery, right? This is a generator, If you wanted 9 volts, just figure all this stuff out. You get a 9-volt battery, basically. All right, cool. Now, so this is a voltage, right? It acts just like a voltage. Well, what's an equation for the current? Well, you know that as well as I do, right? So the induced current, remember Ohm's law. Remember good old Ohm's law? V equals IR, or E equals IR. So therefore, induced current equals induced EMF over R. Well, that's just V, B, L over R. So there you go. And this current is just like our ordinary current. We're just giving it a different name, that's all. But I mean, it's a current, you know? So there. So delta V, which is E induced, is VLB or VBL, who cares? And I induced is VLB over R. All right. Now, cool. So what happens if you get tired and you stop moving this rod? Well, then the velocity is 0, and so you don't get any more voltage or current, right? So the only way you're going to get if you got to keep pushing that rod to the right. And again, there's a force to the left, so it might not be easy, but you got to just keep doing it. All right, so there's two generators. The first one is the coil, and the second one is this motional EMF. Two generators. Okay. Now we've got to learn some laws of nature that help us understand more about why these things work. So let's talk about something called, flux. So flux, we use flux a lot in physics and in other sciences. So this is magnetic flux. Okay, the word flux, it means flow. Flux is Latin for flow. So now you know Latin. All right? So there you go. Okay, so let's say we have a uniform magnetic field. And it extends over an area of 1 square meter. And like always, these lines represent the magnetic field lines. Okay? So what's the flux? Well, the flux is the amount of this magnetic field that's able to go through this area of 1 square meter. Okay? Or you can say the number of field lines that go through this or penetrate this area of 1 square meter. That's what flux is, right? How much of whatever you're talking about, here we're talking about magnetic field, goes through this particular area. All right? You could say if I had an electric fan here, and I had a 1 square meter area, I could say how much air is going through the 1 square meter. You can have flux of air, flux of electricity, flux of whatever you want. Okay, now why do we care about flux? You'll see. Okay. Now, what I want to do now, I want to rotate this 1 square meter area. I want to rotate this plane. Okay, rotate it. So, woo! All right, so I rotated it like this. All right, so what happens to the flux? Am I getting the same amount of magnetic field through this area? Am I getting the same number of magnetic field lines through this area anymore? Obviously not. Okay, so the flux decreased. Okay, let's say I rotate this even more. In fact, I'm going to rotate it so this plane is now parallel to the magnetic field. How much flux is getting through that area if I rotate it like that? 0, right? 0. Okay, so what does the magnetic flux depend on? Well, it depends on the orientation, of this area and the magnetic field. So the orientation is important. Okay, great. Now, we need to come up with an equation for this flux. So let's do that. So 2 vectors are involved. The first one is the magnetic field, no kidding. Now the second one is kind of an interesting thing. So we call it the A vector. The A vector, the magnitude of the A vector is just the area of this plane. So it's 1 square meter, right? But it's a vector, so it has a direction as well. Well, the direction is perpendicular to the area. So in other words, if we were looking at a side view, and here's the plane, so here's the magnetic field, right? And here's the plane, there's this 1 square meter thing. The A vector would always be perpendicular to the plane. So see here, it's this way. See here, it's that way, all right? If the plane were like this, then the A vector would be like that, right? It's always perpendicular to the plane, okay? So that's the A vector. Now, if the A vector is parallel to the B vector, then the flux, we use this funny looking thing for flux, okay? So if they're parallel, the flux, the magnetic flux, is just B multiplied by A. Well, that's nice. Now, let's rotate that area again, like that. Okay, what do you suppose the flux is? And again, let's do the other one too. Let's say that's the B, and then let's say that the plane, okay, so we have all these B lines, and then let's say we rotated the plane even more, so the plane is like this, right? So therefore the A vector is like that, right? Because remember the A vector is perpendicular to the plane. So how much flux is getting through that if this is parallel to that? In other words, sorry, if the plane is parallel to the B, but the A is perpendicular to the B, how much flux is getting through that? 0. Okay, so this is that, when they're, right? When these vectors are parallel, it's that. When these vectors are perpendicular, the flux would be 0, right? Because B is perpendicular to A. Well, how about something in the middle, you know? So what do you think is what's a good equation for flux? What trig function? All right, we've got to use a trig function. What trig function is going to give you maximum flux here, 0 flux here? What trig function? It's cosine, right? Because here the angle between them is 0. Cosine of 0 is 1. Here they're perpendicular. So it's 90. Cosine of 90 is 0. Flux is 0. So cosine. Okay, so that's it. So this is your equation for the flux, magnetic flux. BA cos theta. Right? BA cos theta. So there it is, all right? Magnetic flux. The BA cos theta. Why do we care? You just wait. Why do we care? Well, here's why. Okay, why do we care? Well, think of both of these generators, right? We use magnetism to produce induced currents, right? What did I change in order to produce the induced current? What did I change, or what was changed? There are 3 things that were changed in order to produce the induced current. What are they? Well, you know, I changed on this one, I changed the magnetic field, right? I put it closer and further away, so I was changing the magnetic field. Here, this area was changing, right? As this thing moves to the right, the area is getting larger. And also on this one, remember I took the magnet and this is the coil, I kind of, you know, changed the angle, right? So magnetic field, area, and the angle. All right, so if I change the B or the theta or the A, I was able to produce the induced current. All right? Now, what one physical quantity that we just learned about contains a B, an A, and a theta? Right there, right? B, A, and theta. Okay? So what am I saying? I'm saying that in order to produce an induced current, or an induced EMF, or an induced electric field, what I was really doing, I was changing the magnetic flux, right? the flux through here and the flux through the coil of wire. That's what I was doing. I was changing the magnetic flux. All right? So that's very, very important. Now, for this one, you know, it's pretty simple to figure out the direction of the current, right? I mean, it's sort of obvious. But how about in this one? I mean, how do you, you know, you have this coil of wire, right? You got a coil of wire. I mean, and I was doing this with the magnet. How do you figure out the direction of the current? Is it going this way or is it going that way? I don't know. Well, there's a way to figure it out. And it's called, the guy who figured it out, his name is Lenz. So it's called Lenz's law. Lenz's law allows us to figure out the direction of the current. Okay? Oh boy. All right, now, this is going to be challenging, but you'll understand it after we do some examples. So this is a quote right from the book. Lenz's law. There is an induced current in a closed conducting loop if and only if the magnetic flux through the loop is changing. Okay, we understand that, right? We saw that. Remember here, when I didn't move the magnet, we didn't get any current. So the first sentence is fine. But the second sentence, the direction of the induced current is such that the induced magnetic field opposes the change in the flux. Say that again. The direction of the induced current is such that the induced magnetic field opposes the change in flux. Oh boy. Okay, so this is the important thing, right? Think about it. We're making an induced current. Now what do currents produce? Magnetism, right? So whenever we produce an induced current, we're also producing an induced magnetic field. Now here's the thing. So we have this induced current. It's going to produce an induced magnetic field. The induced magnetic field opposes the change in flux. So that's what you got to remember. Okay? The induced magnetic field opposes the change in flux, and then you figure out the direction of the induced current. Let's do some examples, and you'll understand. I always joke in class, I say, just think of an old person, right? Like old people don't like change, right? I wouldn't know because I'm not old, but anyway. So this magnetic field opposes the change in magnetic flux. Okay? So let's do some examples. Okay, so this is Lenz's law, right? Right here. Okay, so here's a situation. So this is called the ammeter. It measures the current, right? Here's just a coil, you know. Here's a coil of wire with a, whatever, I don't care what, this piece of metal inside or iron or something like that. Here's a magnet. Now, this is not moving, so the magnetic field is not moving. The magnetic field is not changing. The A is not changing. The angle is not changing. So the magnetic flux is not changing. Okay? If we don't have a changing magnetic flux, do we get an induced current? No. Right? So here, nothing. Nothing's going on, just boring. Because there's nothing changing. All right, now let's do this one. Okay, so now we have this magnet, and we're getting it closer to this coil of wire. So you have to think about what's happening to the flux through the coil of wire, right? So, I mean, you know, here's the coil of wire, right? If we're looking in this direction, so we see, you know, so the magnetic field is it's going. So we think about the flux in here. I don't care about out here. We're looking at inside this area, right? So what's happening to the magnetic flux as we move this magnet closer to the coil? Well, obviously it's increasing, right? Okay, so the magnetic flux through the coil is increasing. Wow. We're old people. We don't like change, right? So the induced magnetic field is going to oppose the change. So right now, the magnetic field is increasing this way. We don't like change. We want to oppose that. So that means that the induced magnetic field is going to go this way. Okay? Inside the coil. That's all we care about is inside the coil. All right. So B induced is this way to the left. So therefore, the question is the current going up or down? And you could choose any wire you want, you know. I personally think it's easiest to choose this wire, you know. It's on the outside, right? Okay, so if we want to have a magnetic field point to the left, what's going to be the direction of the current? So now you've got to remember something you learned a while ago. Remember, this is what we learned. Let's say this is a wire. If you grab the wire with your right hand, the current is going in the direction of the fingers. Sorry, the current's going in the direction of the thumb. The fingers point in the direction of the magnetic field. Remember that? So the current's going up, magnetic field goes like this, right? Okay, so look at that wire. We want the induced B field to go this way. So we're going to grab this wire. It's either going to be like this or like this. But again, what we care about is inside the coil. So if we grab it like this, so the current's going this way, the B field is going to go like that. So inside the coil, you've got to admit, the B field is going to go like that, which is what we want. So the induced current points up, okay? Up for this wire, right? Then you can just, you know, kind of go around and around. Okay? Let's do another case. All right, now we're pulling the magnet to the left. So what are we doing to the magnetic flux through this coil? It's getting smaller. It's decreasing, right? Okay. I don't like change. Okay? So the magnetic field is getting smaller, right? It's getting smaller. Oh my gosh, right? Okay, so look at, so the magnetic field points this way, right? It's getting smaller and smaller. I don't like change. So I want the induced B field to go this way, right? Because I don't want change. I want things to stay the same way all the time. Okay? So if I want the magnetic field to go this way, because I don't like change, how am I going to grab this wire? If I want the magnetic field to go this way through the coil. Well, think about it. Just grab this wire, right? Right-hand rule, you know. And what's going to be the direction? What's going to be the direction? Down, right? Agree? Down. Because I grab it, and I grab it down, and it's going like this. So inside the coil, the induced B field points in that direction. So that's Lenz's law. You've got to know how to use it. We're going to use it a lot. So if you're a little bit confused, just kind of go through these exercises, okay? Go through these exercises and make sure they make some sense to you. Let me show you a demonstration before we quit. Okay, let's look at some things here. All right. So here, you can see, okay, this is a magnet. It's super strong. Okay, this is not magnetic, right? It doesn't attract. Okay, this is just, I don't know, aluminum or something like that, right? Just a, you know, hey, what'd you do that for? Ugh. Okay, hold on, I've got to do a little fixing here. All right, good enough. Now, so according to what we just learned, stop. I didn't do a very good job. Okay, so this is a conductor, right? It's aluminum. So if I change the magnetic flux through it, there's going to be an induced current. The induced current is going to produce an induced B field. The B field opposes the change. So watch. Now, what's the deal? I'm not touching it, but yet I'm able to move. I wish this thing would be better. What happened? I was able to move it. Agree? Why was I able to move it? Because my magnetic field, there was my magnetic field, and then there was the induced magnetic field. and they were repelling, right? They were repelling. Yeah. Okay, watch. Or attracting, depends, right? Okay, so is that a magic trick or what? You know? Okay, so I'm actually producing an electric current around this loop. The electric current is producing a B field. The B field opposes the change, and so it's repelling this B field. How do you like that? Pretty cool, right? I mean, it doesn't, you know, again, if you show this to some people, they say, ah, it's magic, because there's nothing touching. There's nothing touching at all. All right, now, let's try it with this. Let's see. Well, you can see there's a slit, right? There's a slit. So I'm not going to be able to get a complete circuit. So what's going to happen? What do you think is going to happen when I do the same thing? Stop moving. Hardly any effect at all, right? I mean, there might be some little currents along this part, but stop, all right? So if I can't really get a complete circuit, there's really not going to be any kind of a current. All right? So that's kind of fun. Let me show you something else which is kind of fun. So let's get rid of this. Okay, now this here, this is a coil. And so it's going to, you know, it's a solenoid, right? Magnet. It's an electric magnet. And this has some iron in it. And so, you know, we talked about solenoids before, right? This is going to be a pretty strong magnet by itself, but if I put this iron in, it's going to even be stronger. Now, this is connected to the wall. The wall is called AC power, so it's alternating. So it's going to be plus voltage, minus voltage, plus voltage, minus voltage. So I'm going to turn this thing on, and we're going to have a changing magnetic field. So if I put this around it, we're going to have a changing magnetic flux through this thing. So there's going to be an induced current and an induced magnetic field, and it's going to oppose this magnetic field. So we're going to have opposing magnetic fields. Well, what happens? Watch. That's pretty cool, right? Okay, here's another one. Another one. This is heavier. Okay, this one. Okay, now how about this one? See the slit? Can you see the slit? See that little slit there? I don't know if you can see the slit. Okay, so what's going to happen with this one? Nothing. All right? This is kind of fun. So this is a wire. So let's put it there. So just to prove to you that we're going to get an induced current along this wire here, let's see if we can make a light bulb shine. All right? So all we're doing is we're changing the magnetic flux through this coil of wire. And that's producing an induced current, which again, makes the light bulb shine. There you go. All right, that's enough for today. Thank you.